lab that we completed on metal activity and reduction potential. And that lab is based on this standard reduction potential table. Uh, and what is a standard reduction potential table? Well, what it does, it lists chemicals in the left-hand column here, okay, based on their ability to gain electrons. So what happens, fluorine is the best species in the gaseous phase to gain electrons based on this reduction potential table relative to actually H plus, which is right here. Okay, everything is compared to H plus on this table. First thing we want to know is that this table is only a partial list. Okay, so this is not a complete reduction potential table. Actually, this would be like maybe 8 or 9, 10 pages long of different species that in water would gain electrons from another species in an aqueous solution. So there are certain facts about this list. First, it's in water, okay, and at 25 degrees, and it's relative to a 1 molar solution of H plus. So these are all based on 1 molar solutions. A 1 molar solution of H plus would be an acidic environment, a very acidic environment, like a 1 molar solution of hydrochloric acid. But what this is telling us is that the species above H plus can gain electrons more readily than those listed below. Okay. The next thing that's important to note is that um, the guys that are listed on the bottom here are the cations of metals in group 1 and group 2. Okay, and you should also note you have aluminum and beryllium, aluminum being a group 13 metal. These ions don't gain electrons that well. And actually, the metals are considered to be electropositive. That means they have very low electronegativities. And they have negative uh, electropotentials. Now, this is a measurement of force that these ions have relative to those listed above them. And again, relative to H plus, which has a value of 0, to gain electrons in these 1 molar solutions. Now, the metals listed to above, like this gold plus 3, could be an example of ions from inert metals. They're very good at gaining electrons. And they're actually listing the number of electrons that they are looking to gain in order to produce the products which are listed on the right. What else is important to note about this table is that the species on the upper left-hand corner here can readily gain electrons off the surface of these chemicals listed in the right-hand column on the right of the arrow. So that would mean that fluorine can easily take electrons away from chloride ions because fluorine, the gaseous species, has a greater ability to gain electrons than the chlorine gas. So therefore, chloride, which contains the same nucleus as the chlorine, will not be able to hold its electrons uh, if fluorine is in contact with the chloride ion in an aqueous solution. Again, this is typically in an aqueous solution that we're referring to. Okay, so what does this have to do with our gel lab? Well, I created 2 gels. One was a clear gel, and in the clear gel, there was oxygen gas in the presence of a weak acid that had H plus ions. So that means these species right here, oxygen gas with the H plus, have the ability to gain 4 electrons and produce water molecules if they come in contact with anything listed to the lower right. So if oxygen plus the hydrogen ions are in the presence of bromide ions, they can actually take electrons away from the bromide ions to force bromide to lose its electrons. How many electrons would it lose? 2 bromides would lose 2 electrons and become bromine liquid. A metal like, let's say, copper, if placed in an environment with oxygen H plus, could possibly react and maybe lose 1 or 2 electrons to produce copper ions. Meanwhile, the oxygen and the hydrogen ions would produce water. So what can happen is the species written to the left of the arrow can take electrons away from any of the species listed to the lower right of the arrow here on this side, all because of their electropotentials. Now, let's say we place the oxygen and the H plus that were in our gel in the presence of cadmium metal. The cadmium metal can lose 2 electrons to the oxygen and then the H plus ions and become cadmium plus 2. But oxygen and the H plus are looking to gain 4. The number of electrons lost and the number of electron gains in these type of what we call redox reactions must always be equal. So therefore, in order to satisfy the need of the oxygen and the H plus ions to gain the 4 electrons to produce the 2 water molecules, the 2 cadmiums would have to lose a total of 4 electrons to produce 2 cadmium plus 2 ions. And when we write the reaction, excluding the electrons, we would end up with our what we call our net ionic equation. What else is in the gel? The clear gel also contained lead plus 2 ions, which are listed here on our reduction potential table. So the lead plus 2 ions were in the gel, and also the H plus ions just above it were in the gel. So that means these ions had the ability to steal electrons from any of the metals listed to the right of the arrow here in these reduction reactions. And based on this electropotential table, we can predict what reactions could happen in the gel. And we could come up with net ionic equations for the possible reactions that occur into the gel. Now, each of these reactions would be separate reactions occurring in the gel. You don't write it as one big reaction, so there's single reactions. So if we were going back to our cadmium example, cadmium can lose 2 electrons to the H plus ion. So 2H plus cadmium would generate hydrogen gas, which is a product of the H plus gaining electrons, and force the cadmium to become cadmium plus 2. And that's how we would write the reaction. 2H plus cadmium arrow produces hydrogen gas plus cadmium plus 2. By putting the ion next to the species, it's understood that the ion is in solution. So for the lab, what you need to do is you need to come up with the hypothesis of what reactions you believe occurred in the gel when you placed the different metals. So what you're predicting is what reactions would take place on the surface of the metals, and based on the reduction potential table. But based on your observations, what confirmations do you have that these reactions are taking place? What results of the reaction are confirming the reactions you're predicting? Now, in the blue gel, the only difference was there was oxygen with the H plus. There was copper ions, copper plus 2 ions. There was H plus ions. So those are the 3 species that were in the blue gel versus the clear gel that had lead plus 2 instead of the copper plus 2. So based on those facts, you need to come up with a prediction, a hypothesis of the types of reactions, write their net ionic equations. These reactions are referred to as cation replacement reactions, or fall into the class of redox reactions. So you need to write down the net ionic equations for your predictions, and then based on the observations from the gel reactions in the vials, come up with what is confirming your prediction.